Welcome to our journey into the world of computer architecture. At its core, computer architecture is the science and art of selecting and interconnecting hardware components to create computers that meet functional, performance, and cost goals. It's like the blueprint for a digital brain, guiding how computers process information, store data, and communicate with the outside world. In this video, we'll break down the key concepts, explore the main components, and see how everything fits together to make modern computing possible. Let's start by understanding what computer architecture really means and why it's so important in our technology-driven lives. Appreciate computer architecture. It helps to look back at how computers have evolved. Early machines were massive room-sized devices with limited power. Over time, advances in hardware and design led to smaller, faster, and more efficient computers. Today, we have everything from powerful desktops to tiny smartphones, all thanks to innovations in architecture. This evolution has shaped the way we interact with technology and has set the stage for the incredible devices we use every day. Every computer, no matter how big or small, is built from a few essential components. These include the central processing unit, CPU, memory, input-output devices, and storage. Each part plays a unique role in making sure your computer runs smoothly. In the next few scenes, we'll dive deeper into each of these components, exploring how they work together to process information and deliver the performance we expect. CPU is often called the brain of the computer. It's responsible for executing instructions, performing calculations, and managing data flow throughout the system. Modern CPUs are incredibly complex, with multiple cores that allow them to handle many tasks at once. Understanding how the CPU works is key to understanding computer architecture as a whole. Inside the CPU, you'll find several important parts: the arithmetic logic unit ALU, control unit, and registers. The ALU handles mathematical and logical operations, while the control unit directs the flow of instructions. Registers provide quick storage for data the CPU is actively using. Together, these elements allow the CPU to process instructions rapidly and efficiently. Instruction set architecture, or ISA, defines the set of commands a CPU can execute. It acts as a bridge between software and hardware, allowing programs to communicate with the processor. Different CPUs may use different ISAs such as x86 or ARM, which influence performance, compatibility, and power consumption. Memory is where your computer stores data it needs to access quickly. There are several types of memory, including RAM, random access memory, and cache. RAM holds data for active programs, while cache provides even faster access for the CPU. Efficient memory design is crucial for smooth performance and multitasking. While memory is fast, it's also temporary. Storage devices like hard drives and solid-state drives, SSDs, keep your data safe even when the computer is turned off. Storage architecture affects speed, reliability, and capacity, making it a key part of overall computer design. Input and output devices connect us to our computers. Keyboards, mice, monitors, and printers are all part of the I/O system. The architecture of these devices determines how quickly and efficiently data moves between the user and the computer, impacting the overall experience. The motherboard is the central hub that connects all components of a computer. It houses the CPU, memory, storage, and I/O ports, allowing them to communicate seamlessly. The design and layout of the motherboard play a crucial role in the computer's performance and expandability. Buses are the data highways that connect different parts of the computer. They carry information between the CPU, memory, storage, and peripherals. The speed and width of these buses impact how quickly data can move, influencing the overall system performance. Every computer relies on a clock to keep everything in sync. The clock generates regular pulses that coordinate the actions of the CPU and other components. Faster clock speeds generally mean better performance, but they also require careful design to avoid errors and overheating. The power supply unit, PSU, delivers electricity to all computer components. Modern computer architecture also focuses on energy efficiency, balancing performance with lower power consumption. This is especially important in laptops and mobile devices where battery life is a key concern. Operating systems act as a bridge between hardware and software. They manage resources, schedule tasks, and provide a user interface. The architecture of the operating system influences how efficiently the computer can run programs and handle multiple tasks at once. One of the most influential computer architectures is the von Neumann model. It describes a system where the CPU, memory, and input-output devices are connected by buses, and both data and instructions are stored in the same memory. This simple yet powerful design is the foundation for most modern computers. Harvard architecture is another important model. Unlike von Neumann, it separates memory for instructions and data, allowing simultaneous access and improving performance in certain applications. This design is often used in embedded systems and microcontrollers. RISC, Reduced Instruction Set Computer, and CISC, Complex Instruction Set Computer, are two major CPU design philosophies. RISC focuses on simple, fast instructions, while CISC uses more complex commands. Each approach has its strengths, and the choice depends on the intended application and performance goals. Pipelining is a technique used to increase CPU performance. It breaks down instruction execution into stages, allowing multiple instructions to be processed at once. This overlapping of tasks helps the CPU work more efficiently, much like an assembly line in a factory. Modern CPUs often have multiple cores, allowing them to process several tasks simultaneously. This parallelism boosts performance, especially for demanding applications like gaming, video editing, and scientific computing. Efficient use of multiple cores is a key focus in today's computer architecture. Cache memory is organized in levels L1, L2, L3 to balance speed and size. The closest cache to the CPU is the fastest but smallest, while further levels are larger but slower. This hierarchy helps keep the CPU supplied with data, reducing delays and improving efficiency. Virtual memory allows computers to use hard drive space as an extension of RAM. This lets systems run larger programs than physical memory alone would allow. The operating system manages virtual memory, swapping data in and out as needed to keep everything running smoothly. I/O controllers manage the flow of data between the CPU and peripheral devices. They handle communication protocols, error checking, and buffering, ensuring that data moves efficiently and reliably throughout the system. Interrupts are signals that alert the CPU to important events like incoming data or hardware failures. The CPU pauses its current task to handle the interrupt, then resumes where it left off. This mechanism allows computers to respond quickly to real-time events. Direct memory access, or DMA, allows certain hardware components to access memory directly, bypassing the CPU. This speeds up data transfers and frees the CPU to handle other tasks, improving overall system efficiency. Expansion slots on the motherboard let you add new capabilities to your computer like graphics cards, sound cards, or network adapters. This flexibility is a key feature of modern computer architecture, allowing systems to adapt to changing needs. Embedded systems are specialized computers built into other devices like cars, appliances, or medical equipment. Their architecture is tailored for specific tasks, often prioritizing reliability, efficiency, and low power consumption over raw performance. GPUs are designed for handling complex graphics and parallel computations. They have many smaller cores optimized for tasks like rendering images or processing large data sets. GPUs play a crucial role in gaming, scientific research, and artificial intelligence. Modern computers are rarely isolated. Networking components like Ethernet cards and Wi-Fi adapters connect systems to local networks and the internet. The architecture of these components affects data transfer speeds, security, and reliability. Security is a growing concern in computer architecture. Features like secure boot, hardware encryption, and trusted platform modules (TPMs) help protect data and prevent unauthorized access. Designing secure systems is essential in today's connected world. Cloud computing relies on distributed computer architecture where resources are shared across many machines. This allows for scalable, flexible services that can handle huge amounts of data and users. Cloud architecture is transforming how we store, process, and access information. Data centers house thousands of servers, each with its own architecture optimized for reliability and performance. These massive facilities are the backbone of the internet, powering everything from websites to streaming services. Efficient server architecture is key to handling the demands of modern digital life. Smartphones and tablets have unique architectural needs. They must balance performance, battery life, and compact size. Mobile processors often use ARM architecture, which is designed for efficiency and low power consumption, making it ideal for portable devices. Wearables and Internet of Things IoT devices are small, connected computers with specialized architecture. They prioritize low-power, wireless connectivity and compact design, enabling new applications in health, fitness, and smart homes. Quantum computers use fundamentally different architecture, harnessing the power of quantum bits, qubits, to solve problems that are impossible for classical computers. While still experimental, quantum architecture could revolutionize fields like cryptography and complex simulations. AI applications require specialized hardware like tensor processing units, TPUs, and neural network accelerators. These components are designed to handle the massive calculations needed for machine learning and deep learning, pushing the boundaries of what computers can do. As computers become more powerful, energy efficiency is increasingly important. Architectural choices like low-power processors, advanced cooling, and smart power management help reduce energy use and environmental impact. Fault tolerance is the ability of a computer to keep working even when parts fail. Redundant components, error-correcting memory, and backup systems are all architectural features that improve reliability, especially in mission-critical applications. Scalability refers to a computer's ability to grow and handle increased workloads. Modular design, clustering, and virtualization are architectural strategies that allow systems to expand as needed, supporting everything from small businesses to global enterprises. Measuring computer performance involves metrics like clock speed, instructions per second, and benchmark scores. These numbers help designers and users compare systems and make informed choices about hardware and architecture. Computer architecture is always evolving. Trends like neuromorphic computing, 3D chip stacking, and edge computing are pushing the boundaries of what's possible. Staying up to date with these trends is essential for anyone interested in the future of technology. Software and hardware are deeply connected. The way software is written can influence hardware design and vice versa. Optimizing software to take advantage of architectural features is key to getting the best performance from any system. Every architectural decision involves trade-offs. Designers must balance speed, cost, power consumption, and complexity to create systems that meet specific needs. Understanding these trade-offs is crucial for building effective computers. Before a new computer architecture is released, it undergoes extensive testing and validation. This ensures that all components work together as intended and that the system meets performance and reliability standards. Rigorous testing is essential for building trust in new technology. Looking ahead, computer architecture will continue to evolve, driven by new applications, materials, and ideas. From quantum computing to AI-driven design, the future promises even more powerful, efficient, and versatile systems. Staying curious and informed is the best way to keep up with this exciting field. We've covered a lot of ground in our exploration of computer architecture. From the basics of CPUs and memory to advanced topics like parallelism and quantum computing, architecture shapes every aspect of how computers work. Understanding these concepts helps us appreciate the incredible technology that powers our world and prepares us for the innovations yet to come.